Hello everyone, my name is Noor Hassan and I am presenting you my method validation project. The title of my presentation is Validation of Troponin T Amino Assay. And the instrument that I'm using is the Roche Cobas 8000. So let's get started. Alright, so my objectives. I wanted to show them the objectives of this presentation before we get started. First thing is I want to introduce you to the instrument itself. I want to go through the modules, give a brief overview. Some of you have already used this instrument if you have a institution that uses it for its chemistry bench. And then afterwards, I want to talk to you guys about troponin T and its clinical significance. The next thing I want to do is go over the validation, as if we were to actually validate this test on the Cobas 8000. And then lastly, I'll answer some pre-made questions at the end. Alright, so this is the Roche Cobas 8000. This is all the modules connected together, and this is what it would look like, just one long structure. In UCLA, we actually have two of these side by side, and so if one goes down, they just reroute it to the other one. So it's comprised of several modules. In the very left here, you have the ISE, 701, 702, and then you have the 502 and 602. And this can run up to 9,800 tests per hour, so when using all of them. And it can do a variety of samples, urine, CSF, plasma, serum, and the whole 9 yards. And it uses photometric for the clinical chemistry part, and then chemiluminescence for the immunochemistry immunoassay. ISE. So this is the ISE. It's the very beginning of that long that I showed you. And it runs the analytes, sodium, potassium, chloride, electrolytes, I should have said. And it's part of, those three electrolytes are part of basic metabolic panel, comprehensive metabolic panel. I mean, it's routine. It's usually always ordered. And it can run up to 1,800 electrolyte tests per hour, so it's a pretty solid module. 702, 701. And you can see it here. And this is the main chemistry module, so all the chemistry is going to be run here: anemia, cardiac, diabetes, proteins. Just the general things that are ran here, and it has 70 reagent positions, so you can load 70 reagents for 70 different analytes to be tested on one module. And if you have two of them connected, you can go even further, depending on the volume of testing that you have. And the difference between the 702 and the 701, they're the same thing, to be honest with you. They're the same exact thing. The only difference is right here, if you can see my cursor, this is a reagent manager, and the 702 has a reagent manager, so you can load the reagents in the 702, but the 701 doesn't have that. Okay. So this is the 502. The 502 can run every single thing that the 702 and 701 does, but it's slower at running them. But the upside of the 502 is that it can run even more analytes than the 701, 702 can. An example being is UCLA uses the 502 module, but we use it for the drugs of abuse and TDM, therapeutic drug monitoring, because the 701 and 702 can't do that. And it's also good to isolate those two, because those two tests are actually really important or those two category of tests are very important, especially if it's involved in like a DUI case or something. It can get very serious, and it's good to isolate those tests on one module, and opposed to mixing it up with all the other general chemistry testing. And this is the 601, 602. This is the one that we're actually going to be using today for our method validation. And it does immunoassays, tumor markers like CA53, and infectious disease, thyroid function, TSH, and then cardiac markers, which include our troponin T. And it can run up to 170 tests per hour. So it's slower, and immunoassays are generally slower testing. That's why in UCLA, when we run quality control, we actually load the immunoassay first, because it takes the longest to get that out of the way. And here's a little presentation. So this is the Cobas immunoassay module. There's obviously a lot of modules here, but for this is the immunoassay module. This probe is the reagent probe, and this is the sample probe. This is the pre-separation, and this is the post. And as you see, the reagent's going in, and it's going into the wells, the samples, and it's being read right over there. And this is it in action. So that was me in that video. I got to show it, lift up the hood, and actually observe it for you guys. So it's pretty cool. Nope. All right, so troponin T. Troponin T, it's part of the troponin complex, which includes troponin I and troponin C. Troponin T is usually ordered if the patient has a history or is suffering from a possibility of having a myocardial infarction, or in common term, a heart attack. So when you have a level of troponin T, it can signal, hey, there's some myocardial damage or something might occur in that field later on. And, you know, it's part of a doctor's diagnostic test when they order it. Method validation. All right, let's start the method validation. So currently at UCLA, we don't run troponin T on our cobas. We use a different analyzer. So we're going to pretend as if we're going to validate troponin T on the cobas 8000, which it can run, but it isn't validated. So these are the steps. First thing is we need to verify our accuracy. So we're gonna do a method comparison between the cobas 601 602 module, the one that you're gonna validate, and a reference methodology that's already been validated, and say the 411 module. Let's say we have a 411 module that's been validated for it. So we're gonna do 20 samples. It's a mix of samples, low, medium, high, on both instruments, and then we're gonna do a linear regression analysis of this, and we're gonna compare to see if there's a correlation between the results, and there should be if it's a good instrument and it's working properly. So here's the chart that I made. As you can see, I have on the y-axis we have the 411 analyzer results, and we have on the x-axis we have the 601. So the 411's already been validated, and the 601 is the trial, and we have a pretty good linear regression here. R squared is 0.99. It's very good. That means there's high correlation between the new method and the old and the already validated instrument. Next, I want to mention systematic error real quick. Systematic error is very important, especially when you're looking at bias, and you can find it by analyzing a chart, either QC or when you're running your tests and you have it together. And I have a chart right here. So we have systematic error. Shift is right here. This would be a shift. And up here you would see a trend. See how it's going in one direction? This is a systematic error, and it's showing bias. It's usually caused by hardware malfunction or debris or something of that sort. So precision is the next step. So for precision, we're going to run at least 2 levels, and they must be tested multiple times. At least 5 days, but people usually go 10 up to 20 days. And then from these repeated trials, we're going to calculate the standard deviation, coefficient of variation, and we're going to see in this slide here. So method comparison, precision. So here we have the 411 and the 601, 602. So we have 3 pooled of each, human serum 1, serum 2, and serum 3 pooled, and then we have the controls, a high and a low. And it was done on both instruments, and you can see here on human serum 1, for example, the mean was 0.04 with a low standard deviation and a 3.4% CV. That's very good. And that's just pretty much showing was there a low different amount of variation between the results, which is good. You want low variation for high precision. And if you look at the 601, 602, you got 0.045 and then 0.001 standard deviation with 2.4% CV. So very good. The results are almost similar, or they are similar, but they're almost the same, I should say. And they have a low CV, which is always good. And you can also verify it with precision experiments. There's 2 kinds that you can do. You can do them both. Most people do both. There's a within-run precision testing, and that's when you get a sample, one sample, you run it 20 to 40 times in a single run, and you do your calculations. People go for 40 because, you know, in method validation, the more data you have, the better it is. You don't have to go with the minimum. You can always go more, because the more data you have, the stronger your case is that, hey, this instrument is good to go. It's good to go live for patient testing. And there's day-to-day precision testing, so you get, you know, I get 20 samples, and then you do it over a period of 10 to 20 days, and you get 20 points of each sample that you have, and you do the calculations. And I have an example here for you. So here's just a table I made up, all fake numbers, but we have our 20 samples here, n, that I ran each sample 20 times over, total 20 times over a period of 20 days. And then this is the mean, this is the standard deviation, and you got a low CV. So you can see you got a low standard deviation problem and a very low CV. So we got some good precision going on here. And these are just equations I wanted to throw up to be useful. Standard deviation, coefficient of variation. Random error affects precision mainly, and it can happen in anything. Maybe the low reagent volume, or there's an environmental difference. Maybe it was too hot in the room or something where the instrument was. And this is an example of a random error. See how everything's good, and then there's just this circle. Like, what is this? Just what happened that day, you know? And here's the magnitude and total allowable error. So this is pretty much a sum of the random and the systematic error, and it's good to show. And a certain amount of it is allowed by CLIA and CAP. That's all we really need to know about that. And then now, after you have precision and sensitivity, or precision and accuracy done, you go for sensitivity. And the test we did for sensitivity was the limit of quantitation experiment, which displays the lowest concentration that can be measured with acceptable precision. And this is an example of it. So we have a 10% cutoff that I have here, and this is the percent CV, and this is the mean of the values. And see how we have the sensitivity is going, and we have let's see here, 0.037, 0.0757 as the cutoff. It's the lowest concentration that can be measured by the instrument, and this is limit of quantitation, and so sensitivity. How low of a concentration can this instrument detect? And I'll go over why that's important soon. And then finally, you want to verify possible interferences. The manufacturer will sometimes have interferences they know of, and they'll put it in their package inserts. And there's other interferences that you can find out. Let's say if you run a hemolytic, lipemic, or icteric specimen in the instrument, you might get a different result. So these two drug interference panels here, I pulled these two off of the package insert that the manufacturer Roche had, saying that these drugs will interfere with the testing if the patient is taking them. And then normal, hemolytic, icteric, lipemic. Hemolytic, you guys know what hemolytic looks like. It's that red, pink tinge on the serum. Icteric is the color, maybe brownish, and the lipemic is cloudy. Next thing you want to do is the AMR and CRR. The AMR is the range of values that can detect and report without it being concentrated or diluted. Some instruments can dilute or concentrate samples. And then the CRR is just... It's a call made by your institution's medical director, and the AMR needs to be validated after recalibration or you change a reagent lot. And this is an example graph I have of it. You see, this is the highest the instrument can measure: concentration, instrument signal response. So right here, when you have these points and it won't go any higher up, that's saying this is the limit of the high, as you could say. And then finally, reference range and interval. So reference ranges are different based on the laboratory's geographical location and the local patient population. So a laboratory in LA is going to have a different patient population than, say, one in Berlin. For Troponin T, maybe not so, because they're all the same when it comes to, if you have myocardial issues, you're going to be the same in Berlin or Los Angeles. But I wanted to put that in there. And there's two approaches you can do to establish reference range: parametric and non-parametric. And I have an example of non-parametric here. By the way, parametric you just use a 95% confidence interval, whereas non-parametric, you would use the 2.5 and 97.5 percentiles, and that would be your cutoff for your reference interval. So if you have 160 samples, your sample number 4 and your sample 156 would be your cutoff for your reference range. There's miscellaneous, LIS interfacing, making sure the LIS works with the Troponin T, if there's communication between the LIS and the instrument, and then reporting to CAP that you're running this so they can send you testing kits. And then you want to update the SOP and write the SOP for training purposes for CLS that are running it. And then once that's all done, you just validate, and that's it. It's approved once it's signed off by your medical director. Now, I want to go with questions. Question number 1. Why does AMR need to be recalibrated just because you use a different reagent? It's the same reagent, I thought. Like, come on. Well, you can tell I wrote these. Well, yes, it's the same reagent, but different lots can affect different the results. They make lots in batches, the manufacturer does, and they sometimes use real serum when they make their reagents, and you might get different results, and you want to make sure that the instrument's still giving you correct results. So you need to recalibrate the AMR. How exactly can interferences affect the result of the test? So back with that slide that was showing the lipemic icteric, or if they're taking certain medication. Well, I mean, it could vary. Some can raise the value, some can lower the value, some can mask it. It depends. It really depends on what the drug is doing. It depends if the instrument can read a very lipemic sample. Most won't. Most would. The Cobos example would, when I was in my chemistry rotation, if we had a lipemic sample, it would flag it, and we would have to do a dilution. However, some tests do not require it, or you cannot do a dilution. You'd have to do an ultracentrifugation. But it's just a little example. But it can interfere either way or mask it. Do all method validations require a limit of quantitation sensitivity experiment to be done? Well, limit of quantitation doesn't always have to be done depending on what your analyte is. For troponin T, it needs to be done. And the reason being is for troponin T, the really low values, like if you have a 0.03 troponin T level, that's indication of a possible myocardial damage. So that's a really low amount to be detected. So the low levels are extremely significant in this case. Most people should have 0 to 0.01 to be normal. Anyone above that, there's some issue going on. So you really want to detect the low levels when troponin T is being validated. Why are low levels of troponin significant for detection? Well, like I said, I kind of answered 3 and 4 in that. But you know what? Limit of quantitation doesn't always have to be done. And troponin T is significant because, yes, if the patient has a rising troponin T level, 0.02, then you test them again. They're getting 0.025. You test them again. They get a 0.031. Then you're like, thinking the physician's thinking to himself, hey, this person's suffering from a myocardial tissue damage. We better start treatment to reverse the troponin T levels, or to reverse any damage that's done, because you don't want the patient to have a heart attack. And question number 5: how long does it take to validate a new test methodology from start to finish? Will I be retired by the time it's finished? Well, I think it takes about a month to 3 months, depending on how quick you want that method to be validated, how much work you want to put into it, depending on how much data you want to gather for that instrument, or for that method validation. Like I mentioned earlier, the more data you have is better. And despite CLIA and CAP requiring their minimum amounts, most institutions, they have their own prerequisites. They usually go for stricter standards than what the law requires of them. So sometimes you need to go above the minimum amount of data. Maybe you need to get a lot of data. Maybe instead of a 10-day day-to-day testing, you gotta do a 30-day day-to-day testing. Maybe instead of 20 points, they want 60 or 100 points. Maybe they want method comparison with not just one institution, but a different reference laboratory. It depends. It all depends on the institution. So I would say a month to 3 months is a good measure. And by the way, I just want to give a special thanks to everyone at UCLA for helping me with this Thomas, Vincent, Kevin, and Lindsay, and to my lab partner, Anna Marie. Thank you, everyone, and I hope you appreciated this representation. I hope you enjoyed this presentation. And these are just some references. All right, have a good one.